Welcome to the presentation of our Sigmund paper on optimizing the trade-off between privacy and utility in data provenance. My name is Daniel Deutsch, and this is joint work with Ariel Frankenthal, Amir Gilad, and Yuval Moskovich. Data provenance is a record of the transformations that data undergoes, for instance, for query evaluation. It comes in many flavors with many models that have been developed over the years, and it has been shown useful for many applications, including explaining query results, hypothetical reasoning, namely finding out what would be the result of a query if the database would change, probabilistic query evaluation, and many others. There are many lines of research on data provenance, including works on developing new models, better solutions for storing provenance, for the complexity of generating provenance, algorithms that use provenance for applications such as those mentioned above, and so forth. Let's illustrate the concept of provenance via a simple example. So consider this query that looks for people who like dancing and are interested in music. This query, when evaluated over this simple database, yields two query results, the output 1 and 2. These are the identifiers of the relevant people. The provenance essentially links input tuples to the output tuples. So in this case, it says the provenance of the output tuple 1 is p1.h1.i1. P1, H1, and I1 are identifiers of tuples in the input, and the dot means intuitively that they have been jointly used to generate this particular piece of output. As I said, there's lots of research on multiple aspects of provenance, and in this work we shed light on a particular aspect that has been studied to a lesser extent, and that's the interplay between provenance and privacy. So where privacy comes into play is as follows. Consider a database owner who may wish to explain a specific query result. So they wish to publish provenance for one tuple or two tuples or a few tuples of the output. They may either wish to do so or be mandated to by regulations such as GDPR or other. And yet they may be reluctant to reveal the underlying query because it's proprietary and they don't want to reveal the entire logic. They just want to show explanations for particular query results. Can they do that? So one question is, to what extent does publishing provenance really reveal the underlying logic, the underlying query? And if the answer is that it does reveal it, can one publish some form of provenance for a query output or for a subset of the query output while keeping the query confidential? In general, the answer to the first question of whether publishing provenance reveals the underlying query, well, it reveals quite a lot about it, at least for the models that are commonly used in the literature for provenance. So to illustrate that, let's look again at the query that we looked at before, and notice that even if we are given just one output tuple along with the provenance, then we already know quite a lot about how the query behaves. So just by looking at this P1 times H1 times I1, we know that the query joined persons' hobbies and interests. And if we further look at two tuples, then we can identify commonalities in the provenance atoms that participate in the provenance of the two tuples. And we can see that the constant dance appears both in H1 using the provenance of 1 and in H2 using the provenance of 2. So it wouldn't be a wild guess to assume that the underlying query talks about the constant dance in this attribute. We don't know that with certainty, but it makes sense, especially if we see more examples where dance appears. Same thing goes for music. And in this case, with two plausible guesses, we can focus on the real query just by looking at these two output examples. So you may wonder if this is the case in general, or maybe this is the case here just because the query is simple and the provenance model we've used is quite elaborate. There are other provenance models, for instance, lineage, that do not detail the way that the tuples are connected. So for instance, the lineage of such output with respect to this query would just be the set P1, H1, I1. And maybe if the query is more complex, then there are things that are hidden in the provenance. It turns out that there are things, but not that many. So we studied this previously in a completely different context, the context of query by example. So query by example systems are systems where users try to build a query, non-experts try to build a query by giving examples for their desired output. And we've shown in previous work that if we ask the users to give us just a little bit more information, not just the examples of their output, but also explanations for why these output tuples really interest them, then we can reverse engineer the query with great accuracy, even for a few examples. And the explanations that user gave us in this context actually correspond to models of provenance. So they correspond to how provenance or why provenance, and in subsequent work of Gilad and Moscovich, they corresponded to lineage. And in all such cases, we have been able to reverse engineer even complex queries such as those that appear in the TPCH benchmark with good accuracy. Lineage is a bit more challenging, but still there's only so many plausible ways in which the tuples can connect in a reasonable query. So that's good news for the query by example systems because it allows better focusing on the query that the user has in mind. But it's bad news if you are the owner from our previous example who's trying to publish provenance as explanations, but still trying to hide the underlying query. So it means that really, if we publish provenance, we reveal quite a lot about the query. So towards the solution, we propose to leverage a notion that we've developed in a paper from Sigmund of last year, which is called provenance abstraction trees. So provenance abstraction tree is a node label tree where the leaves are labeled with annotations from the provenance expression, and internal nodes are labeled with concepts that generalize them. So for instance, these are annotations of tuples from the input database, and they all come from Facebook. And Facebook is a social network, etc. So we have this hierarchy of concepts where at the bottom, at the leaves level, we have the provenance annotations. So then this defines a notion of abstraction. An abstraction is simply replacing an annotation such as H1 with an ancestor in the tree, such as Facebook. Obviously, when we do that, we have obfuscated the original provenance, so we lost some information. We're not sure if the actual tuple that was used was H1 or H4, or maybe it's some tuple that's not from the hobbies table, but rather came from Facebook and appears in a different table. We lost some information in the provenance, and at the same time, we gained some privacy with respect to the original query, because now maybe we're not sure whether the query looked at dances or trips, or maybe it looked, or whether it looked at hobbies at all. So more formally, given a provenance expression and the label tree whose leaves are labeled with provenance atoms, an abstraction maps each occurrence of an atom to an ancestor. And then a concretization is the kind of inverse of abstraction. It maps an ancestor back to some leaf. And of course, we're not sure that we are going back to the same leaf. So if we map the expression to P1 times Facebook times I1, a concretization may map Facebook to any leaf in its subtree, and we get different concrete provenance expressions. So intuitively, the set of concretizations that are induced by a given abstraction dictates the loss of information incurred by the abstraction. And we need to measure this, we need to quantify this loss of information in some way. In our paper, we use the entropy of this set, but we can support other functions as well, and we discuss this in the full version of the paper. As for privacy, recall that our goal is to obfuscate the underlying query. There may be other privacy goals, but in this paper, this is what we're trying to obfuscate. And thus, our privacy model counts the queries that are consistent. And when we say consistent, we mean that the query generates the examples as part of its output, along with at least the correct provenance, meaning that the some concrete provenance that is consistent, that is a concretization of the abstracted provenance, appears in the explanation generated by the query when evaluated over the database. So these are the possible queries given the abstracted provenance. There is a bit of a technicality, and we need to restrict attention to queries that are most interesting, namely that are connected. We don't want queries that whose join graph is not connected, because these are not plausible queries, so it makes little sense to count them towards a breach of privacy. And also, we want to gain some kind of diversity in the queries that we are counting, so we restrict attention to tight match queries, namely those that are inclusion minimal. And we say that the query is inclusion minimal if no query that is strictly contained in it is consistent with the set of examples. So we impose some constraints over the queries that we count, and then we count the number of queries that are consistent with some concretization of the given abstract provenance. Another aspect is what class of queries we are looking at. And this class of queries may be SPJ or SPJU, SPJU plus aggregates. The choice of the class of queries also affects other notions in the problem setting. And so this is a parameter to our problem definition. So the optimization problem that results is as follows. We capture loss of information by the entropy of possible concretizations. We capture privacy by the number of matching queries after restricting attention to connected inclusion minimal queries. And we look for abstractions that achieve a given privacy threshold while incurring minimal loss of information. We also study the dual problem, which may be also of interest. And we parameterize this whole thing by the target query language, whether it's conjunctive queries, UCQs, or queries with aggregation. In terms of complexity, a first easy observation is that there are exponentially many possible abstractions obtained by any combination of a choice of ancestor for each provenance atom. And it turns out that the problem is indeed NP-hard. It's NP-hard even if we restrict attention to SPJ queries. The hardness is in the provenance size due to these possible combinations. And it's shown via reduction from Berthe's graph. The components of our solution then involve how do we traverse abstractions. As we said, there are exponentially many, but we need to traverse them in a smart fashion. For each abstraction that we are considering, we need to compute its level of privacy, and we need to compute the level of loss of information that it entails. So for traversal of abstractions, we work our way bottom up in the abstraction tree in a greedy fashion, and that leads to abstractions with small loss of information being examined first. For each abstraction, we then need to compute the privacy and the loss of information. Loss of information computation, for definition, is quite straightforward. We just look at a set of possible concretizations. But computing privacy is more challenging, so we need to know how many consistent queries are there for all possible concretizations. So we do that based on algorithms from this earlier work on a query by example enhanced with explanations that I've mentioned before, in which this counting was done for different provenance semi-rings and different query classes. This is still quite costly to do, especially if we're considering that there are maybe many concretizations to consider. So we optimize this process by looking at one example at a time, discard concretizations that are not interesting, namely they are disconnected, and by caching results for concretizations, bearing in mind that different abstractions may yield the same concretization. We've implemented our solution in a system prototype called PITA, Privacy for Provenance Abstraction. The user inputs a query over a dataset. The query is evaluated using a provenance-aware evaluation engine, and the user gets output and provenance. Then they choose what part of the output and the provenance they wish to share. They need to design this abstraction tree, the DBA can do that, and they need to set the privacy threshold they're interested in. The system then performs this optimization algorithm to choose the best abstracted provenance to propose back to the user. So here's a quick example over the IMDb database. The user chose a couple of tuples for which they're interested in showing the explanations, set the privacy threshold, and the system proposes an abstraction. In this case, instead of talking about a particular person, we just show that the person is that this is a person who was born between particular ages, and instead of talking about a particular movie in the provenance, we just say that it's a comedy produced between 1990 and the year 2000. And we show some options for the queries in order to allow the users to really inspect whether the privacy level they are interested in is suitable for them, and so forth. So this is an interactive process. We've conducted experiments over TPCH and IMDb, and we've shown that our solutions scale well with respect to the privacy threshold, with respect to the abstraction tree size, and with respect to some aspects of the provenance size. For instance, we can deal with queries that have multiple joins, and our heuristics are useful in this respect. We have conducted the usability experiments where we've shown that the abstracted provenance allows to really obfuscate the query while still being useful for applications, in this case, hypothetical reasoning. There are still some computational challenges involving large-scale provenance. And then we need to differentiate between different kinds of large-scale provenance. If we start with union of conjunctive queries, then observe that the size of each monomial is bounded by the size of the query, which would typically not be that large. So one possible heuristic is to abstract each monomial, each explanation separately, and then mix and match them, possibly using user interaction. With aggregates, the story is more complicated because a single explanation may involve multiple values coming from tuples in the group over which aggregation was performed. And that's an open problem, how to efficiently handle aggregation in practice. So to conclude, we've developed a framework for measuring privacy and utility of data provenance, and for optimizing the trade-off using the notion of provenance abstraction. There are many possible notions of privacy and utility. We followed some of them in this paper, and others are explored in the full version of the paper that is available via Archive, but there's much work to be done in this respect. Specifically, one possible desideratum is to maintain privacy of the underlying data rather than the query. And that's something that should be further explored in terms of the measurements that we are using for privacy. Thank you very much.